Hi students, so this is lecture number 2 in unit number 3 in digital logic design, and the topic name is ripple adder subtractor using 2's complement subtraction method. Okay, so in previous lecture we discussed about a ripple adder and 4-bit ripple subtractor. Okay, in this lecture the object of this video is I would like to discuss about a ripple adder subtractor by using 2's complement method and advantages of disadvantages of this particular circuit. Okay, so this ripple adder or subtractor, what does it mean by ripple adder or subtractor? Okay, so instead of using two different circuits for two different operations, if we can use one single circuit for both operations, that means either addition operation or subtraction operation, we can use only one single circuit. Okay, so by using again full adders. Okay, so in this ripple adder subtractor circuit, and if you can see the circuit diagram is existed like this way. Okay, so in this circuit diagram, which is a little bit lengthy, but and if you can observe in this circuit diagram, okay, so what you observe here, so here one of the operand is resistor B, in that resistor, basically the general definition of resistor, which is used to store the bits. Okay, so the resistor B is 4-bit resistor, that means which is used to store 4 bits only, and those bits are B0, B1, B2 and B3. Okay, so another one, their complements also, B0 bar, B1 bar, B2 bar, B3 bar. Okay, now so the resistor which is used to store 4 bits, and 4 bits are B0, B2, B3, like that way. And for any operation, addition or subtraction, so like resistor B, again we are having resistor A. The resistor A also, which is a 4-bit resistor which is used to store 4 bits only, and the 4 bits are A0, A1, A2, A3. Okay, and these bits are applied to 4-bit parallel adder. Okay, so in previous lecture we are discussed how the 4-bit parallel adder works. Okay, now in real applications, in reality, the 4-bit adder is available in the form of IC, integrated circuit. So for 4-bit parallel adder, the available IC is 74LS83. For this circuit diagram I am using, so the circuit diagram utilizing 74LS83 IC. So the 74LS83 is nothing but 4-bit parallel adder, which is consisting of 4 full adders. And we know very well each full adder is consisting of 3 bits, 3 inputs and 2 outputs. Okay, so according to that full adder construction, all 4 full adders are connected in cascading form, and for this 4-bit parallel adder, it is consisting 2 operands. One is operand resistor B, and another one is resistor B, and another one is resistor A. Okay, in addition to that, if you observe, so from resistor B to parallel adder, you may observe some number of gates. So especially in this row, 4 types of gates are there. So these are all gates belongs to AND gates only. Okay, and again second row 2, 4, 6, 8 some number. Okay, and these are also AND gates. Okay, and 9, 10, 11, 12, these are also nothing but OR gates. Okay, so 3 rows are there. In 3 rows, first 2 rows are filled with AND gates, and third row is filled with OR gate. Okay, and they are numbered also 1, 2, 3 like that way. Okay, and if you can observe, the one of the most important, that is control pin, that is add or subtractor. What does it mean? To control the entire circuit, so we need to use one control input. That control input is nothing but add or subtractor. Okay, so according to this control input, the circuit may performing different types of operations. So in this particular circuit, which is used to perform two types of operations, one is addition, another one is subtraction. Okay, so according to the control input, the circuit diagram performing either addition operation or subtraction operation. Okay, now what type of input we may apply to this control pin? Okay, and it is very easy. And if you are supposed to apply 1 for this control input, and the circuit will act as a adder circuit. If you are supposed to apply 0 for this control input, the circuit will act as a parallel subtractor. Okay, how? Okay, let me explain one by one. Okay, so first of all, I am taking one example, that is, if I am applying 1 for this control input, what happens? Okay, so if I applying control input 1, and this 1 is carry forward to this first AND gate is 1, and third AND gate is 1, and fifth and one of the input is 1, seventh one is one of the input is 1, because this in this particular 1, 3, 5, 7 all are belongs to AND gates, and each AND gate is consisting of two inputs. Okay, one input is connected from control input, adder, subtractor, and another input is connected from B0, B0, B1, B2, B3. Okay, so according to the truth table of AND gate, so if any AND gate output is said to be 1, if both the inputs are equal to 1, then only the output of AND gate is equal to 1. So according to the truth table, now I am supposed to apply the particular truth table condition. So for this AND gate 1, one of the input is 1, and another one is B0, irrespective of what is the value of B0. Okay, so here one of the input is 1, another one is B0. Okay, so what is the outcome of this AND gate? Outcome is B0 only. Okay, if B0 is 0, output of 1 is 0. If B0 is 1, output of one gate is also 1. Similarly, for AND gate 3, what is the output here? Output is I may expect B1 only. And for AND gate 5, I am expecting the output is B2. And for AND gate 7, I am expecting output is B3. Now, see, there is another path is also there, and it is applicable to the second row. Okay, in that second row, what type of gates are there? AND gates. Again, AND gates, and those are named as 2, 4, 6, 8. Okay, but here, so the control input is converted, again applied to the inverter, and the output, the inverted output is applied to the AND gates 2, 4, 6, 8. Okay, now I am taking the control input is 1, so the inverting value of 1 is 0, and this 0 is applied to one of the input for AND gate 2 and 4 and 6, 8 as 0. And second inputs are connected to B0 bar, B1 bar, B2 bar, B3 bar. All are connected to the inputs of second AND gate, fourth AND gate, sixth AND gate, eighth gate. Again, I am recollecting the truth table of AND gate. What is the truth table of AND gate? Again, if any one of input is 0, the output of AND gate is 0. Okay, either both the inputs are 0 or any one input is 0, the output of AND gate is 0. So here in second row, the AND gate one of the input is 0, so I need not to consider the another input is B0 bar. Okay, obviously the output of AND gate is 0. Okay, similarly the output of fourth AND gate is 0, output of sixth AND gate is 0, and output of eighth AND gate is 0. Okay, now I'll come into third row. Third row, which all gates are belongs to OR gate. Okay, in OR gate, so it is consisting two inputs. One input is collected from AND gate 1, and another input is connected from AND gate 2. Okay, one of input is from AND gate 1 is B0, and another one is 0. And similarly, one of the input of an OR gate 10 is B1, another output is 0. Similarly, for 11th OR gate, so one of the input is B2 and 6th AND gate output is 0. Okay, so I'm expecting the output is B2. Why? Because according to, again, I'm recollecting the truth table of OR gate. What is the truth table of OR gate? So if any input, if both the inputs are equal to 0, then only my output is 0. Otherwise, my output is always equal to 1. So here is the same thing. So here I am getting B0, B1, B2, B3. Whatever the value of B0, B1, B2, B3, the outputs of all OR gates are equal to B0, B1, B2, B3 only. See, finally, all by taking AND gate, add or subtracting one input, and the OR gate produces outputs are B0 and B1 and B2 and B3. And already we applied A0, A1, A2, A3. Okay, just recollecting the structure diagram of a circuit diagram of parallel adder, which resembles the same. So that, so by taking control input add or subtract is 1, this IC or this particular 4-bit ripple adder or subtractor will acts as a ripple adder. Okay, and next one, if I supposed to consider if we supposed to apply control input is 0, now what happens? Same, if control input is 0, indicate the first row 1 3 5 7 all are disabled. Why? Because they are getting the value as 0 0 0 0. So by considering the truth table of indicates, the outputs of these indicates are 0 0 0 0 irrespective of B0, B1, B2, B3 values. Why? Because if any value, if I indicate any input is equal to 0, the output is 0. And next, so the control input is 0, the inverting of control inverter is 1. Now this 1 is applicable to indicate 2, 4, 6, 8. All inputs are applicable to the same value 1, 2, 1, 1, 1, 1. Okay, and another inputs are B0 bar, B1 bar, B2 bar, B3 bar. Again, the outputs of AND gate 2, which is equal to B0 bar, outputs of fourth gate is B1 bar, and 6, this is B2 bar, and this is B3 bar. Okay, see again the same as like a previous one. In previous case, the first case, AND gate 1 produced B0. Now in this case, AND gate 2 produces some input B0 bar. Okay, so here the value is 0. Output of AND 1 gate is 0 because the one of the input is 0. That's why output is also 0. Similarly, this output, particular AND gate 3 is 0. This one, for this output of AND gate 3 is 0, and output of fourth AND gate is B0 bar. So the output is B0 bar. Okay, see here B1, B0 bar, B1 bar, B2 bar, and B3 bar. Okay, so like this one. So here outputs by applying control input is 1, control input is 1. Now I am getting B0 bar and B1 bar and B2 bar and B3 bar. Okay, so B1 bar, B0 bar, B2 bar, B3 bar, and my control input is 1. Why I am getting 1? Because here my adder or subtractor control input is 0. This 0 is applied to here, and this 0 inverted here, and this 1 is again applied to this 0 is 1 and applied to where? Here C1 and is 1. Okay, and according to the 4-bit triple subtractor circuit diagram, here it obeys 2's complement form. Why? Because so here the B0 bar and B1 bar, B2 bar, B3 bar. Even though you are applied B0, B1, B2, B3, but after calculation, after a simplification, we get the inputs in the form of B0 bar, B1 bar, B2 bar, B3 bar, which is added with this one. So it satisfies the 2's complement subtraction method, and with the circuit will acts as a 4-bit ripple subtractor. Like this way, so the 4-bit ripple subtractor adder will works under the control of adder or subtractor. Okay, so once again I repeat, if my control input is 1, so this ripple adder or subtractor will act as a ripple adder. If my control input is 0, this ripple adder subtractor will act as a ripple subtractor. Okay, so this is the working principle of ripple adder and ripple circuit. Okay then, so and this is my second lecture, and I hope you understand the concept. Thank you.